Hello, I'm Professor Ryan O'Donnell. I research the theory of quantum algorithms, statistics, probability at Carnegie Mellon University. What excites me most about the field of quantum computing is the fact that I eventually realized over the course of my learning about quantum computing and quantum mechanics that quantum mechanics is basically like probability 2.0. It's like a generalization of the laws of probability to a situation where you have non-commutative random variables. And this made me really excited because I really like probability in computing, but a lot of things in probability have already been done. But now with probability 2.0 or quantum mechanics, you get to do it all over again. So if you're sad that George Boole proved the union bound in basic probability 175 years ago, well, you can try to prove the quantum union bound in this day and age. And it might be even more interesting and exciting than the basic probability version. Actually, I have to admit that I'm more of a lone wolf. I don't have too many collaborations with other PQI faculty members, but this is mostly because the people I collaborate with most are my students. So we have a lot of great students here at Carnegie Mellon, and I've collaborated a lot with my PhD students and also with undergraduates on quantum computing research. So these students are my main collaborators. The results I'm most proud of in quantum are my work on quantum tomography, which is more of like a fancy name for the quantum 2.0 version of learning a probability distribution from samples. So it's the problem of learning a quantum state from many copies of the quantum state. So this is actually one of the first problems I really worked on in quantum computing. I got into it because of my graduate student, John Wright, who is also getting into quantum computing. And we decided to work on this problem. And it turned out to be both really hard, but also really fundamental and filled with like a lot of really beautiful mathematics. And so I learned so much over the course of this research on it about representation theory and KPZ and Young diagrams and all sorts of cool stuff. And the results we managed to prove turned out to be pretty sharp for this fundamental problem. So I'm really satisfied how this project turned out. When I'm working with students or postdocs, I guess there's a couple of kind of modes. So I like to think that when we're collaborating together on the research part, the math part, I'm kind of like a laid-back, fun guy. It's a good time to bat ideas back and forth about math. I guess on the other hand, when it comes to writing it up, I'm a little bit more picky, shall we say. I really like to make things as precise as possible and write things as cleanly as possible when the research is done. So this might be a little exasperating, but hopefully you had some good times along the way. Well, maybe I shouldn't say this out loud because I'm not totally sure I'm going to follow through on it, but I am planning to write a new book about quantum computing. You might think, aren't there like already 5,000 books about quantum computing? Like, why do we really need a new one? That's true, but I hope it'll be a little bit different. It's going to be based on the undergrad course that I teach here at Carnegie Mellon about quantum computing, and I have some slightly different ways of doing things. So I hope I follow through on it, and if I do, I hope you like it.